You see it every single day. You've seen it since the moment you were born. It's so constant, so familiar, that most people never stop to ask the question, why is the sky blue? Not white, not black, not green, blue. What if I told you the answer involves a Victorian scientist who literally shouted at smoke, a Nobel Prize winner who didn't believe his own discovery at first, and a phenomenon so strange that it changes the color of the sky depending on where you stand and what time of day it is?
All right, a Victorian scientist shouting at smoke. That's not what I expected from a question about the sky. I assumed the answer was something simple, like the sky reflects the ocean or something.
That's one of the most common misconceptions out there. A lot of people think the sea is blue because it reflects the sky, or the sky is blue because it reflects the sea. Neither is true. The real answer is far more fascinating, and it starts with a fundamental question about light itself.
Okay, go on then. What is light, and what's it got to do with the color of the sky?
So, light from the sun looks white to us, but it's not really white. White light is actually a mixture of all the colors of the rainbow: red, orange, yellow, green, blue, and violet, all traveling together. Isaac Newton proved this back in 1666 when he passed sunlight through a glass prism and it split into a rainbow of colors on the other side.
Right, the famous prism experiment. So sunlight is secretly a rainbow, but that still doesn't explain why the sky picks blue out of all those colors.
And this is where the story gets really interesting. Each color of light has a different wavelength. Think of light as waves, like waves on the ocean. Red waves are about 700 nanometers long. Violet waves are about 380 nanometers. Blue sits at around 450 to 490 nanometers. And this difference in wavelength is the entire key to why the sky is blue. Because when these waves of light hit something, and by something I mean the tiny molecules of gas in our atmosphere, they don't all behave the same way.
What do you mean? What happens when light hits the atmosphere?
This is where our Victorian scientist enters the story. His name was John Tyndall, and in the 1850s and 1860s, he was obsessed with understanding why the sky was blue. At the time, nobody had a proper scientific explanation. People had theories. Some thought it was moisture in the air, others thought it was dust, but nobody had proven anything.
And this is the man who shouted at smoke?
Well, not exactly shouted, but close. Tyndall built an ingenious experiment. He created a long glass tube and filled it with smoke and various gases. Then he shone a beam of white light through the tube and watched what happened. And what he saw was remarkable. The light scattered inside the tube turned blue. The beam of light that passed straight through the tube turned reddish-orange.
Wait, he recreated the sky inside a glass tube?
Essentially, yes. He created a miniature atmosphere in his laboratory. The smoke particles in the tube were scattering the shorter blue wavelengths of light in all directions, while the longer red wavelengths were passing straight through. He had just demonstrated why the sky is blue during the day and why sunsets appear red.
That's brilliant. But you said he shouted at it.
The shouting part comes from another experiment where he demonstrated that sound waves could affect the behavior of flames and particles. He was known for dramatic scientific demonstrations at the Royal Institution in London. He'd literally shout at sensitive flames to show how sound waves worked. He was quite the showman, but his light scattering experiment was his greatest contribution.
So Tyndall figured out that small particles scatter blue light. Is that the full answer then?
Not quite. Tyndall got the observation right, but he thought the scattering was caused by tiny dust particles or water droplets in the air. He couldn't explain why the scattering favored blue light so strongly. For that, we need another scientist, and this one won a Nobel Prize for it.
Who was that?
Lord Rayleigh. His real name was John William Strutt, but he became the third Baron Rayleigh. In 1871, he published a paper that mathematically explained exactly why shorter wavelengths of light scatter more than longer ones. He proved that the scattering wasn't caused by dust or water droplets at all. It was caused by the gas molecules themselves, the tiny nitrogen and oxygen molecules that make up our atmosphere.
So it's not particles floating in the air, it's the air itself that scatters the light.
Exactly. And here's the key formula. Rayleigh showed that the amount of scattering is inversely proportional to the fourth power of the wavelength. That sounds complicated, but it means that shorter wavelengths scatter enormously more than longer ones. Blue light scatters roughly 16 times more than red light.
16 times more? That's not a subtle difference. That's massive.
It's huge, and that's why the effect is so dramatic. When sunlight enters the atmosphere, the blue wavelengths get scattered in every direction by the gas molecules. They bounce around the sky like ping pong balls. So when you look up, you're seeing scattered blue light coming at you from all directions above you. The sky looks blue because blue light is being redirected towards your eyes from everywhere above you.
But wait, you said violet light has an even shorter wavelength than blue. Shouldn't the sky look violet then?
Brilliant question. And you're absolutely right. Violet light does scatter even more than blue. Mathematically, the sky should look violet. This puzzled scientists for quite a while.
So why doesn't it?
There are two reasons. First, the sun actually emits more blue light than violet, so there's simply more blue to scatter in the first place. Second, and this is the fascinating part, our eyes are much more sensitive to blue than to violet. The cone cells in our retinas that detect color respond much more strongly to blue wavelengths. So even though violet is being scattered everywhere, our eyes are essentially filtering it out and perceiving the sky as blue.
So the sky is technically violet, but our biology makes us see it as blue? That's incredible. We're essentially seeing the sky through a biological filter we don't even know is there.
That's exactly it. If we had different eyes, say the eyes of a bee, which can see ultraviolet light, the sky would look completely different to us. The color of the sky is as much about the observer as it is about the physics.
That's a genuinely mind-blowing thought. Okay, so Rayleigh explained the blue sky, but what about sunsets? You mentioned Tyndall saw reddish light passing through his tube. Is that the same principle?
It's the exact same principle, just taken to an extreme. During the middle of the day, sunlight travels through a relatively thin layer of atmosphere to reach you. Enough blue light gets scattered around the sky, and enough of the other colors still reach you directly, that the sun appears white or slightly yellow and the sky is blue.
Right, that makes sense so far.
But at sunset, the sun is near the horizon. Its light now has to travel through a much thicker layer of atmosphere to reach your eyes, sometimes up to 30 times more atmosphere than at midday.
Oh, so by the time the light reaches you, almost all of the blue has been scattered away.
Precisely. The blue light gets scattered out long before it reaches you. The only wavelengths that survive the long journey through all that atmosphere are the longest ones, red and orange. That's why sunsets are red and orange. You're seeing the light that's left over after the atmosphere has stripped away all the blue.
So a sunset is basically what happens when Rayleigh scattering goes into overdrive. The same mechanism, just more of it.
Perfectly put. And this also explains why sunsets are more vivid after volcanic eruptions or in areas with high pollution. More particles in the atmosphere means more scattering, which means even more blue light gets removed, leaving deeper, more intense reds and oranges.
That explains those incredible sunsets you see in photographs from after major eruptions. The 1883 Krakatoa eruption supposedly produced extraordinarily vivid sunsets around the world for months.
It did. Some historians even believe that the vivid red sky in Edvard Munch's famous painting The Scream was inspired by the Krakatoa sunsets visible from Norway in 1883. The volcanic ash in the upper atmosphere turned skies blood red across Europe.
Wait, really? The Scream might be a painting of a Krakatoa sunset? That's an amazing connection between science and art.
It's one of those wonderful intersections where physics, geology, and art history collide. But let's keep going because there's more to the story of the blue sky.
There's more? What else is there?
Think about this. If the sky is blue because of Rayleigh scattering, what color should the sky be on Mars?
Mars has a much thinner atmosphere, right? So maybe less scattering? A darker blue or even black?
Good logic, but actually the opposite. The Martian sky is typically a butterscotch or pinkish color during the day, and at sunset, the sky on Mars turns blue.
Blue sunsets on Mars? That's completely backwards from Earth.
It is, and it's because the Martian atmosphere is filled with fine iron oxide dust particles, rust, essentially. These particles are much larger than Earth's gas molecules, so they scatter light differently. The dust scatters longer wavelengths, reds and oranges, during the day, making the sky appear pinkish. But at sunset, when the light passes through more of the dusty atmosphere, the larger particles actually scatter the red light away and allow more blue light to pass through.
So Mars has the opposite of Earth's effect. Red sky by day, blue sky at sunset. That's extraordinary. Same basic physics, completely different result because of what's in the atmosphere.
And it gets even more interesting when you look at other planets. On Uranus, the atmosphere contains methane, which absorbs red light, so the planet appears a pale blue-green. On Titan, Saturn's largest moon, the thick haze of organic molecules creates an orange sky. Every world has its own sky color, determined by the same basic principle: what's in the atmosphere and how it interacts with light.
We think of a blue sky as normal, but it's actually just Earth's particular recipe. Different atmosphere, different sky.
Exactly. And here's one more thing that most people don't realize. If Earth had no atmosphere at all, if you were standing on the surface of an airless world like the moon, the sky would be completely black, even during the day. The sun would be a blindingly bright disk against a pitch-black sky full of stars.
Because with no atmosphere, there's nothing to scatter. No scattering, no blue. Just the void of space.
The Apollo astronauts described exactly this. They could see the sun, the earth, and the stars all at the same time against a perfectly black sky. It's one of the most alien things about being on the moon. Daytime looks like nighttime, except with a blazing sun.
That really drives home how special our blue sky is. It's not just a color, it's a sign that we have an atmosphere, that we have something between us and the void. It's literally the color of our protection.
That's a beautiful way to put it. And it circles back to something remarkable about this whole story. The blue sky is something so everyday, so constant, that almost nobody questions it. But when you dig into the why, you find Victorian showmen shouting at flames, Nobel Prize-winning physics, the biology of human vision, volcanic eruptions inspiring famous paintings, and alien sunsets on other worlds, all hidden behind a color you see every time you look up.
I will absolutely never look at the sky the same way again. From Tyndall's smoke-filled tubes to Martian blue sunsets. What a journey.
And that's all for today on The Why Behind Everything. Thank you for listening.
Next time, we're asking a question that starts with a sound you make every single day, but have never understood. Why do we yawn? And more mysteriously, why is yawning so incredibly contagious? The answer involves empathy, evolution, and a brain-cooling theory that changes everything.
You won't want to miss it. Make sure you're subscribed and hit the bell so you never miss an episode. We'll see you next time.